Good evening, everyone. Namaste and a very warm welcome to all our respected guests, scientists, academicians, researchers, faculty members, coordinators, students, innovators, and technology enthusiasts joining us from across the country. I am Anjali Gandham, student coordinator at KIYE Foundation, and it is my privilege to host today's S-Talks Lecture 20. Before we begin, I kindly request everyone to introduce yourself in the chat box by mentioning your name, college name, and branch. It will be wonderful to know where everyone is joining us from. It is truly inspiring to witness participants from different parts of India united by one common passion science, innovation, research, and nation building. KIYE Foundation is a non-profit organization dedicated to inspiring young minds through science, technology, aerospace, defense, innovation, entrepreneurship, and leadership. The foundation was established by Mr. Naresh Senior with a vision to bridge the gap between academics and industry by connecting students with eminent scientists, defense experts, researchers, entrepreneurs, and professionals. Inspired by the vision of Bharat Ratna, Dr. APJ Abdul Kalam, the missile man of India and the people's president, KIYE Foundation is committed to nurturing scientific thinking, innovation, and youth empowerment. His dream of transforming India into a developed and self relevant nation continues to inspire every initiative of the foundation. Through lectures, workshops, internships, industrial visits, research initiatives, and career guidance programs, KYE Foundation continues to empower thousands of students to become future innovators and responsible nation builders. STOC stands for Space, Aerospace, and Futuristic Technologies. This flagship initiative aims to ignite curiosity among students and provide them with direct interaction with India's leading scientists and technology experts. Our vision is 52 lectures, 52 speakers, 52 topics, 52 weeks of inspiration. Every session is designed to inspire learning, innovation, and excellence. Our theme for today's session is Quantum Technology Shaping the Future. Quantum technology is transforming the way we think about communication, computing, sensing, and security. Today's session will give us a glimpse into the exciting possibilities of quantum science and its potential to shape the technologies of tomorrow. So, my dear friends, get ready to explore the quantum world and the future it holds. Before introducing our distinguished guest speaker, let us watch a short audiovisual presentation highlighting the vision, mission, and remarkable initiatives of KIYE Foundation. I request one of our coordinators to kindly play the AV. Thank you. If the presentation inspired you, don't forget to drop a rocket in the chat. Now I invite our student coordinator, Mr. Abdul Rahman, to briefly share his journey with KIYE Foundation. Rahman, the virtual stage is all yours.
Thank you, Anjali. Hello, good evening, everyone. I am Syed Abdul Rahman, a student coordinator at KAY. I am really excited to speak and share my experience with KAY Foundation. My journey at KAY is actually started right where you are sitting in the audience. I was just an observer at first. By seeing and the amazing work KAY was doing made me join in. I began as volunteer where you got the opportunity to contribute the prestigious event such as Kalam Space Convention 2025. Over time, by helping with more events, I grew into a role of student coordinator. This event helped me to improve my communication skills, teamwork, leadership, confidence, and event management skills. I also had the opportunity to interact with scientists, students from different institutions. Today, I am proud to be as an active student coordinator at KY. Through this journey, I had learned how to organize events, coordinate with teams, manage responsibilities, and work under pressure. Every event has helped me grow personally and professionally. KY Foundation has also encouraged students to think beyond academics by providing opportunities to participate in meaningful events, interact with experts, and develop practical skills that are essential for our future careers. This achievement became possible because of the guidance, encouragement, and support of our mentor, Dr. G. Satish Reddy sir and Naresh Indian sir. I sincerely thank them for being in me and motivating me to achieve this opportunity. I also extend my heartfelt thanks to entire KI Foundation team for providing students with platform to learn, innovate, connect with experts, and grow as a future leaders. My journey with KI Foundation has been truly life changing. I am proud to be a part of this organization and I look forward to contribute to my more events while inspiring other students to make the best use of this real world opportunities. Thank you and have a insightful evening.
Thank you, Rahman, for sharing your inspiring journey and valuable experience with KIY Foundation. We truly appreciate your thoughts. My dear friends, the moment we have all been eagerly waiting for has finally arrived. Before introducing our esteemed speaker, let us take a moment to know about the organization she represents, TAQBIT Labs. TAQBIT Labs is a deep tech company based in Bengaluru, working at the forefront of quantum technology and cybersecurity. The organization focuses on developing innovative quantum security hardware and software for applications across government, defense, and enterprise sectors. TAGBIT Lab is actively working in areas such as quantum key distribution, quantum random number generation, quantum communication, and quantum sensing with the vision of transforming advanced quantum research into practical and secure technologies. One of its significant recent achievements came in July 2026 when DRDO completed military field trials of a scalable fiber based quantum key distribution system architected and productized with TAGBIT as its industry partner. This work represents an important step towards building large scale and multi hub quantum communication networks in India. And today, we are truly privileged to have with us a young researcher who is contributing to this exciting journey in the field of quantum technology. And now it is my immense pleasure and privilege to introduce our esteemed speaker, Miss Aditi Das, scientist at TAQBIT Labs. Miss Aditi Das is a scientist and quantum technologies researcher with expertise in quantum communication and quantum sensing. She holds an M.Sc in physics from NIT Karnataka and currently works as a scientist at TAQBIT Labs, where she is involved in the security and theoretical aspects of quantum key distribution along with research in quantum sensing. Her contributions include research publications, two field patents, and proposals for quantum sensing programs for the defense sectors. We are truly honored to have a scientist, Miss Aditi Das, with us today to share her valuable knowledge, research experience, and insights into the fascinating world of quantum technology. So, my dear friends, let us give our esteemed speaker a warm virtual welcome by filling the chat with welcome, ma'am. Ma'am, On behalf of KIYE Foundation, we sincerely thank you for accepting our invitation and taking the time to be with us. We are truly excited and eagerly looking forward to learning from your knowledge, research experience, and expertise in the field of quantum technology. The virtual stage is all yours, ma'am.
Thank you for that introduction. It was amazing. Uh, I'll just get started with my presentation. Uh, just let me know if there are any technical problems on my part. Uh, yeah, is it visible?
Yes, ma'am, it is visible.
Okay, okay. So hi, as you know by now, I'm Aditi Das. I have been associated with TAQBIT Labs. Uh, my work mostly involves theoretical research, but as we'll know, get to see, experimental research is also very important for quantum technologies. So today I'm here to sort of introduce, because we only know about quantum computing when it comes to quantum technologies, I want to give a little bit of an overview about what is necessary to understand quantum technologies and a little bit of other quantum tech that we should be excited about. So, right before we go ahead with what quantum mechanics is, what quantum tech is, we should understand why we care about quantum technologies. Uh, we might think of it as a future technology, which is not true. We have been using quantum technologies for a while now. Uh, Atomic clocks are using GPS satellites. We face the problems of quantum mechanics daily. Like we know that chips are getting smaller and smaller by the day. So there are problems when you make things at such small scales. For getting an MRI test, we use quantum, that is a quantum technology. And then again, there are quantum computers and quantum communication, which is a future. It will be in the future, and obviously we are working on it at present. We have very impressive achievements in the field at present, and we'll go through it slowly. So, to get the story started, we need to know why quantum mechanics came into being. We have to understand that. So, at the end of the 19th century, sort of in late 1800s, people thought that there was nothing else left to explore in physics. Michelson is a very well-known scientist. He had claimed that we know everything that we have to know in physics. It's all a matter of making better measurement devices, how precise we can be with it. The ideas of classical physics are whatever we have studied till our classes 10, 11, we call it classical physics. There are some notions in classical physics. First is it is continuous. And the second one is that it is predictable. So what do I mean by predictable? We have equations like Newton's kinematics. If we know what are the starting conditions, then we can arrive at a prediction which is going to give us the acceleration, the time taken. We have studied all this. So classical physics is essentially predictable. Then some problems started coming along, but to explain that problem, I have to explain some preliminary concepts. So, by nature, every body emits radiation. Even humans, as humans, we emit radiation. This is an infrared camera capturing a tennis player. So, by nature, every object will radiate thermal radiation. Thermal means owing to its temperature. And objects as we see it, the colors of those objects is because of the light reflecting off of it. So whatever colors get absorbed by that object, and what gets reflected is the color we see. So for a yellow pencil, only the yellow color gets reflected. That is why I see it as being a yellow pencil. So this is exactly the point in history where problems started. Uh, there are some specific objects called black bodies, which if we put any sort of electromagnetic radiation, it is going to absorb it all and it is going to reflect nothing. So hence physics is very cleverly named it black bodies. But when scientists were studying these black bodies, whatever classical physics gave us could not explain the nature of these black bodies. So what classical physics gave us was that with increasing frequency, the radiation intensity should just keep on increasing. If we agree with this, if this is what was actually happening in reality, then as we heated an object more and more and more, as we put more energy into it, it would just become invisible, because then the frequency would increase and go into wavelengths of frequencies that the human eye cannot see. But here is where quantum mechanics comes into play. The laws of quantum mechanics give us that it will not go into the outside the visible wavelength. So what does exactly quantum mechanics give us? So uh, Max Planck, in the year 1901, gives us the groundbreaking result that energy is not continuous; it is discrete. So what do we mean by it being discrete? It is, let's say, so we are around discrete things in our real world as well. So let's take the example of stairs or a shelf. You cannot put an item between two shelves, or you cannot stand between two stairs, you'll fall, right? So what Max Planck gave us in 1901 was that energy does not act like a slope. It does not continuously increase or decrease. It increases in steps, it decreases in steps. So this equation E equals to NHF. Are the steps. N is our integers, so 1, 2, 3, and so on. So this is what the groundbreaking result was. And people took this, scientists obviously took this idea. There was Niels Bohr, and this is another. This I chose this because we do get exposed to this topic, right? Photoelectric effect. At the end of class 12, we get exposed to this. So that is how essentially quantum mechanics began, right? So Einstein took this idea and applied it to light. Einstein said that light energy also comes in the form of packets of energy, quanta of energy, called photons. So this equation, we have seen all this, right? Work function, energy, maximum energy. We have seen these equations. What does E equal to HF mean? E equals to HF or NHF means that light energy gets divided in form of packets of energy. This is how we have seen a photoelectric effect as well. Students who have gone through class 12 physics, if you are not, I'll just give you a brief understanding of the problem. What happened when scientists shown they put light on metal surfaces, they saw electrons were being ejected. Now the problem was classical physics gave us the prediction that if we put more light on it, or more intensity light, so we just increase the brightness of the light, then the energy of the electron should increase, right? But this is not what was experimentally being observed. What was being observed was the frequency of the light was affecting the energy, the kinetic energy of the electrons. So this again got explained by Einstein using this concept of quanta. So from these three, and I'll say three because Bohr also gave us the concept of orbitals, discrete orbitals. So these three topics, or even these two topics, give us a common ground, which is discretization of energy levels, which means that energy is in the form of steps, right? So this is a simple harmonic oscillator, which is essentially just a pendulum. It oscillates to and fro. So for a quantum harmonic oscillator, so an object that a quantum object that vibrates or oscillates is going to have an energy in this form on the right. Then we come to this. The quantum mechanics gave us discretization of energy. This is where one important aspect of it ends. Then we come to again familiar grounds, young double slit experiment. This was essentially to tell us the properties of these things like photons, electrons. Are they actually particles and or are they actually waves? Because there was a huge debate in early 1900s, late 1800s and early 1900s. Is light particle? Is light a wave? So if light was a particle, then this was the sort of property we would observe, that there's two slits and we keep shooting light at it. And like particles or sand particles or any particle we have seen in our day-to-day life, how it would behave is it would simply go through the two slits and get collected on the screen behind it. This is how particles would we are expected to behave. But how would light behave if it was a wave? Then there is a phenomenon called interference that happens for waves. So essentially, the different waves, they interact with each other. They cancel out in some parts. They add up in some parts, and there are alternate bands of bright and dark regions. This is what is expected from a wave. Now let's see what exactly happened for light. Light. This is what happened. So when light was individually thrown, when it was, I'll play it again. When it was individually thrown at a screen, we see that the nature is random in the beginning. But when, let's say, more than 1,000, when a lot of light particles with light was thrown at it, then we see that wave nature coming back. This is absolutely mind blowing. So if we throw light at single photon, we call it photon, single photon level, if we throw it, then it becomes random. But when there's thousands and more than thousands, then that wave nature comes back. So how do we explain this? How can it be a particle and a wave at the same time? Right. So scientists settled for the nature of wave particle duality. So scientists settled with light being wave and particle both. So when it is observed as a wave, it shows wave-like particles, wave-like nature, and when it is observed as a particle, it shows particle-like nature. And de Broglie was the scientist who said that this is applicable for all matter. Regardless of anything, it is applicable to all matter. So if we throw a ball, even that is going to have some wavelength, right? So this de Broglie's hypothesis again becomes true when we observe the same nature with electrons. So electrons, we know, whenever we study, electrons are small particles, but comparatively they're huge. Compared to photons, they're huge. So how can we have always studied electrons, photons, neutrons, them to be particles, right? How can they exhibit wave-like nature? But they do. In the same way, if we throw individual electrons at those two slits, initially in the scale of hundreds or 500s, then we are going to see that it's random. Like we can see here, right, in B and C, it's fairly random. But when there are more than thousands, more like higher orders, then we start seeing that same pattern, that same interference pattern, right? So there comes a problem here. We call that problem the measurement problem. We'll get to know why it is a problem. Now let's say you want to observe this whole phenomenon. You want to prove. You say that you are not going to accept this thing that matter is both a wave and a particle at the same exhibits both the properties of wave and particle, and you say I am going to put detectors close to each slit. We can do that. That is an experiment, right? We can do it. So what happens when we do that? Yeah, I'll just mute it. So what happens? One second. Yeah, what happens when we put a detector near one of the slits? So that this detector is going to give us the information which slit does the thing go through? Is it the left or the right? This detector is going to give us that information. What happens as soon as we put the detector, before the detector was placed, it was acting like a wave. As soon as we put the detector, it starts acting like a particle. It's like a naughty kid at school where they're getting like a naughty kid at school, and the teachers complain to the parents, and they are absolutely the best kid in the house, right? So it's like that. As soon as there's an observation, uh, the particle or the wave, it changes its nature completely. So that is why we call it a problem, measurement problem, because we'll never really know. We have to settle for that wave particle duality. Now comes a scientist called Heisenberg, who gives us another very, I'll say, confusing result. It is a little confusing, and also, again, a great theory, obviously. So Heisenberg gives us uncertainty principle. To understand uncertainty principle, we'll sort of use a classical scenario. Let's say there's a highway and there are cameras fitted. So if we ask the question, where is a car? Where is a particular car? And versus what is the momentum or what is the velocity of the cars? It is a fairly difficult question. Like, how can you, if you know the velocity of a car perfectly, you might not be able to say the position that perfectly. But we can do it. If there are very good cameras and a lot of equipment, then it can be classically possible. But at the quantum level, it is absolutely not possible to give us an idea of position and momentum simultaneously. If we know position very well, there's going to be more error in knowing momentum, and vice versa. If we know momentum very well, then there are going to be more errors in knowing position. So let's say see an illustration of the whole thing. Uh, this is what frequency is, right? How many sheep do you see? That is what frequency is. So there can be two types of waves, where there are more vibrations and where there are less vibrations. If there are less vibrations, we call it frequency, less low frequency, and more vibrations is more frequency. So let's say, sorry, I am sorry about that. So let's say we have a wave like this. Where do we say the position is? We cannot really point out, right? But we know the frequency of this wave, and hence we can guess the momentum. But what do we say the momentum of this wave is? It is here, it is here, it is everywhere. But let's see what happens for this wave, right? This is called a localized wave. We can say the position of this wave. We can talk about the position of this wave, but we don't really know what the momentum, what the frequency of the wave is going to be, right? So in again some mathematics, I will show you. This is called uncertainty principle that Heisenberg gave us. This might look a little confusing, but this just means this delta x means that error that I said, or we say it uncertainty in knowing momentum, and this uncertainty of knowing position. We cannot know these both quantities perfectly, right? Now we come to actual quantum mechanical principles. So I gave a historical overview, right? So now we come to some quantum mechanical principles that you will hear when the topic of quantum technologies come up. But before we go to that, just one slide of math to show how quantum states are represented. It is represented by something called Dirac notation. It is a column vector, and if we square these values, then we get the probability. Probability of what? So let's say there's two colors of balls. These analogies are not going to be good, but I will try. So there's two colors of balls. With A square probability, there's a red ball, and B square probability, there's a blue ball. So this is how we would represent the state of that ball. Fine. Let's go to superposition, which is one of the interesting, only one of the interesting principles in quantum mechanics. So I talked about probability, right? So superposition tells us that a system can be in a sort of an addition of these all of these probabilities, right? And when we measure it, the moment we measure it, it falls into one of those outcomes. So I know this is going to be very confusing. Let's see a video illustrating the whole thing. So this is a quantum state, right? It can be, so this quantum state or this system is going to exist as a sum of all its possible outcomes, measurable outcomes, right? So how do we do that? So there's this quantum state which can be 0 or 1 or a superposition of 0 and 1. So what does this superposition mean? So let's say there's a half and half probability. Like this is a general quantum state, but let's see. Yeah, this is what I meant by that A and B. There's half probability of the quantum state being 0 and half probability of the quantum state being 1. This is how we represent it, right? So what will it mean? What does this half and half probability mean? It means that 50% of the times when we measure it, it is going to give us 0. And the other 50% of the times, it is going to give us 1, right? But here comes so there can be different probabilities. Here comes the measurement problem back. So once we measure it can be 0, the next moment it will be 1, it will be 0 again. So it means that we can never directly measure a superposition state. Whenever we measure a superposition state, it is going to give us a classical outcome. So going back to the red ball, blue ball example, which I'm not a fan of, but we make do. So 50% of the times it can be a red ball, 50% of the times it can be a blue ball. Whenever we measure it, it is going to give us a red ball or a blue ball. Right? It is those are things we are used to. Those are classical states, is what we call it. But the difference between probability, simple probability, and a quantum state is that from the beginning itself, it is in that superposition, in the quantum form. Whereas in a classical setting, it can only be a red ball or a blue ball. It cannot be both at the same time. Right. This is, I am very sure we have all heard about it in pop culture. This is very common, Schrodinger's cat. So Schrodinger actually gave this example to sort of prove how stupid superposition is, the concept of superposition is. But sadly for him, he was correct. Superposition is actually a physical phenomenon. So the thought experiment he gave was that let's keep a cat in a box with an atomic experiment or a nuclear experiment, right? Which has like 50-50 chance of happening. So with the so if that nuclear thing, like a nuclear particle is if it emits a nuclear particle, then it puts down a hammer and breaks a poison. So essentially there's a 50% chance of a cat being dead and the cat inside being dead because of the poison, and 50% chance of the cat being alive because the poison is not let out into the air. So Schrodinger said, see, like this sounds stupid, but until you open that box, that cat is 50% dead and 50% alive. So it is dead and alive at the same time. How is that possible? Right? But that is exactly what happens in quantum mechanics. So if we go with a system in the quantum level, so let's say an atom, and we want to know there's an atom and where the electron is. So randomly it will be moving around, right? So if we try to observe it by opening the box, then the electron gets stuck in one place. So we'll never actually observe this electron moving around like that. So here, this is again to talk about it, but this is exactly what the measurement problem is. That we, for some reason, we cannot really measure a superposition state. It is always going to, we are always going to see the outcome, right? So, yeah, sorry. Yeah, so this illustration is about entanglement. So entanglement is called spooky action at a distance. That name was given by scientists. To understand what entanglement is, we have to understand the concept of spins. So in brief, in just one sentence, if I say spins, then certain quantum objects have this property because of angular momentum. Angular momentum is momentum, but for something that is rotating, right? Something that has a rotational motion. It has angular momentum. So it was observed that like electrons have this intrinsic. So intrinsic means by nature it has this angular momentum, and because of this angular momentum, there's direction. There's a we can associate a direction with it. So it can be up, down, left, right, all directions, all possible directions, right? So when two particles, what now? Let's come to what entanglement is. If two of these quantum objects are entangled, then there can be a property like this. If we observed one, the one on the right, it gives us up, then automatically it will give us down on the other one, right? And if we observe down on the right one, then up on the left one, right? And it is, and you might ask that how is it entanglement? Maybe it's by pure choice, but we know that it's entangled because of measurements in other directions. So whatever this one on the left does, the other one on the right will do opposite. So if we measure right direction spin on the right one, then left on the left one. So that is how we say that it's entangled, right? The measurement on one quantum object is going to affect the outcome of the other quantum object, right? So this is essentially what entanglement is. And now I come to the second part of my talk, which is quantum technologies. Now, whenever we talk about quantum technologies, everyone talks about only quantum computing. But there are other avenues as well, a lot of other avenues which quantum technology is made out of. So quantum computing is also obviously one of the main ones. There's quantum communication, which my company TAQBIT Labs works on. And there is quantum sensing. So let's come to what quantum communication is. So there are two parties, Alice and Bob, and they want to talk to each other secretly, right? So there are multiple ways of doing it, but one way is for Alice to give a key to Bob. So a key is just a lot of random numbers, and the actual message that Alice wants to send to Bob, Alice will do some mathematical, I'll say manipulation to her message with that random string of numbers, which is called the key. So Alice will mathematically manipulate her message with that key to make essentially gibberish. To someone who doesn't know the key, it is going to look like garbage, right? But when Bob gets the key, and that we call it encryption and decryption. So what Alice is doing is called encryption, and what Bob will do is called decryption, right? So when without the key, it is going to look like garbage to a third party, right? And when Bob gets the key, he's going to decrypt it and get the final message, what Alice is trying to say to Bob. We can do that process without quantum communication as well, but there are some advantages that classical systems cannot give us. So what are those? What is the primary advantage? The advantage is that if there is a third party, if there is a listener, then Alice and Bob are going to know that there is a listener. So in movies, you get to see like there's a spy, or or the main character is a spy, and they try to tap their phone. This tapping is what is called eavesdropping, right? So the people are talking and there is a third person trying to listen into the conversation. That is called eavesdropping. So if this eavesdropping happens in quantum communication, then the people involved are going to know. So how does this happen? It's because of two quantum principles. Quantum mechanics gives us the rules that these cannot happen. Okay, so the first one is measurement problem. I have already mentioned that if it is in a superposition state, then we can never see the superposition state. It falls into one of those outcomes. So if this eavesdropper or this third person Eve, if she's trying to manipulate the things somehow, then it falls into one of those outcomes and Alice and Bob get to know. And the other one is no cloning theorem. There are certain rules like this which tell that no, you cannot do that. You cannot do. It's a no-go. We call them no-go theorems, which are not allowed by quantum mechanics, right? So it says that you cannot copy unknown states. So if there's an unknown file on your computer, you can just copy and paste it into your file, into your folders. But in quantum mechanics, if you don't know something, know a state, you cannot copy it. So I'll discuss one protocol. So there is this property of light. This protocol is called BB84, by the way. BB84. B is Bennett and Brassard, and it was invented in 1984. So BB84 protocol. So there's this property of light that it vibrates. So the electric field, light has electric field and magnetic field, right? So this vibration, the direction of the vibration of the electric field gives us a property called polarization. So depending on the direction they vibrate, we say they are linearly polar, horizontally polarized, vertically polarized, diagonally polarized, and anti-diagonally polarized. So vertically polarized light can go through a vertical polarizer. It's called a polarizer, or like a polarizer is something that polarizes light, right? So it is going to, if light in no direction is coming through the polarizer and the polarizer's direction is vertical, then the light that goes out of the polarizer is going to be vertical. So only vertical light can go through vertical polarizer, right? And let's see what will happen if, what will happen if a vertically polarized light tries to go to a horizontal polarizer? It is going to get stuck. It is going to bounce back and get stuck, right? What happens if we send a vertically polarized light through a diagonal polarizer? Then 50%. So what happens is some light is going to go through it. Okay. So essentially now what Bob and Alice do is that Alice sends these polarized in different directions, these polarized lights. So once she's going to randomly, once she's going to send diagonal light, once she's going to send anti-diagonal light, horizontal light, like this she keeps on sending, right? Oh, this is an illustration that I found it very, when I was studying this protocol, this is the image that came to my mind. We used to see this show called Takeshi's Castle, and no, I don't remember, but there used to be the show on Pogo, essentially, and there were contestants who had to go through a wall. So you had to be the exact shape as that hole in the wall to go through. So this is exactly how polarizers and polarized light works. So if it is horizontal, it tries to go to a horizontal polarizer, it will go through. But if it is diagonal, for this show also, if they were a little off, they did go through. So if they are vertical and there's a diagonal polarizer, then some of the light will go through. So this is exactly what they use, Alice and Bob, they use these polarizations of light. And Alice will send in these directions, this horizontal, vertical, diagonal, anti-diagonal. She's going to send it like this. Bob is going to have a polarizer. He's going to measure in 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 not in exact these horizontal vertical directions, but he's going to measure it if it is a cross or if it is a plus, right? He has only these two options. Alice has the four options. Bob has these two options. If it was in plus, which means it can be horizontal or vertical, and if it was cross, which means if it was diagonal or anti-diagonal, right? So, and then Alice and Bob, after doing this whole thing, what do they do? They check between each other on a public channel. Public channel means a phone call or any conversation that is open to the public. They are going to call, and then they're going to check which of these matched. If it was in the plus or if it was in the cross, whatever doesn't match, they are going to cross out, and whatever is going to be left, they're going to make a key out of it. Okay. Now, where does Eve come into it? So, what Eve is going to do, she's going to sit in between Alice and Bob. She's going to take Alice's photons and send it to Bob. So, she has something like a system like this, right? She has her own polarizer and she has her own way of sending polarized light. But the problem here that is going to be the main problem is going to be Eve doesn't, she will know this. She will not know what exactly Alice is sending, if it is horizontal, vertical, diagonal, anti-diagonal. And this is going to cause something called an QBER, which is an error. So Alice and Bob are going to see in because of nature itself, there is going to be some error, right? In every experiment, there is some error. But there is a threshold value. So we say that if it crosses this QBER threshold, then there is an eavesdropper present. And this is how we get to know for quantum key distribution. There are other such protocols as well, but this is a very basic and very nice way to start. So this Eve is because she doesn't exactly know what exactly Alice is going to send. She's going to make some mistakes in putting her in sending the light. Right? Yeah, she's going to also randomly send light, and then Alice and Bob, when they discuss, they're going to see that there are more errors, and then they're going to know. They're going to get suspicious that there is someone in between. And then next comes quantum computing. This is a fairly well discussed field. I will give a introduction to it, but I believe there are way better resources to explain quantum computing because it's a very well discussed field. So for quantum computing, we know for computing, normal computing or classical computing, we call it. There is something called bits. So it's 0, 1 values, right? So what happens is there are fixed 0, 1 values. This is what we use for classical computing. For quantum computing as well, there is going to be a 0 and 1. 1 second. Yeah, there is a 0 and 1. Like here we can see on the top and the bottom, there is a 0 and 1, but it can be all possible quantum states between that 0 and 1. So it can be, imagine it to be a sphere. It can be that arrow can point it at any direction. So this is what we learned from superposition. So using the superposition and entanglement, this and interference, which we get from Young's double slit. So these three properties gives us a thing called quantum parallelism, which means that we don't have to run one calculation at a time. We can run, it's almost like running multiple calculations at the same time. Right? It's like running multiple calculations at the same time, right? So this is what these three things, superposition, entanglement, yeah, it's like running it multiple times at the same time. So it's way faster than we could ever imagine it to be. We can ever make it at a classical level, right? And then comes quantum sensing, which is my last topic for today. So quantum sensing is using these quantum states or quantum objects to detect or feel the presence of things which we might not be able to do with our existing devices. So this is one field that I personally know because of my research. So this is called quantum illumination. How it works in just a very brief way is that, remember those entangled particles, those entangled pairs, where one particle's nature, how it gets interacted with is going to affect the other particle as well. So these, we use this entanglement, we use one of these entangled, let's say photons, let's say we are using light itself. So we are going to use one of these entangled photons, send it to some place, a target. It comes back, we do a measurement on it, and we can say if there was actually something or not. So where does this need come from? Essentially, there are things called radars and lidars. Radar is radio detection and ranging, and lidar is light detection and ranging. So what is their task? The task is to find out if there is an object which is ranging, it is asking the detection, which is asking the question if something is there, and then ranging give us the distance for how far that object is, right? So we are doing it at a quantum level. We are trying to ask the same questions, but with more precision. We want more precision. So this is what essentially what quantum sensing is, what quantum illumination is all about. But quantum sensing is asking that question: will we be able to detect things that we have not been able to with our existing devices? So we already have quantum sensors today. It's not a research field anymore. We have been using it for a long time. Like I mentioned, atomic clocks, that has been put into satellites a long time ago. So one of those quantum sensors that we have, which is also an active field of research, but we also use them, is NV center sensors. So so there's a diamond is a crystal, right? So there's going to be geometrically placed atoms, and NV center means nitrogen vacancy. So what happens is there is going to be some vacant space in this diamond, this crystal structure. Vacant means there's nothing, it's empty. So there's going to be this vacancy, and there are impurities. Obviously, nothing is going to be 100% pure. So there are going to be nitrogen atoms from which the electron is going to come and sit in this hole, in this vacancy, essentially. And it is going to emit a pink color. Okay, it's called a fluorescent pink color. So what scientists do, this is uh, this is exactly what a sensor is supposed to do, right? So what scientists do is that they bring materials, or they take it to places where there are changes in magnetic field. It can very precisely detect changes in magnetic field. So when like a magnet is a big thing, it's a huge thing. But let's say there's some change in the magnetic field, and the color of the pink fluorescent color, the intensity of it changes according to the change in magnetic field. So this is like a quantum, this is doing sensing at a quantum level, right? So these were, yeah. So as there's change in magnetic field, you can see the change in the intensity, the brightness of the pink color. So that is it. I wanted to introduce what goes behind quantum technology. So superposition entanglement, I hope you can, if someone asks you, if you know, you will be able to talk about it. And because the most widely discussed field is quantum computing, I wanted to talk a little bit about what other quantum technology fields are there. There are a lot. There are quantum materials and a lot of other fields. These are the main three fields that are being looked into currently. And these are also obviously interesting to talk about. So I hope you understood what quantum technology requires and where it is headed. So that's it on my part. And if you have any questions, please go ahead. I'll answer any questions right now.
Okay, ma'am. Uh, Thank you so much, ma'am, for such an insightful and inspiring session. We will now begin the interactive question and answer session. Participants are requested to pose their questions in the chat box. Kindly keep your questions brief and relevant to today's topic. Ma'am, we have an interesting question from our coordinator Hasini. As quantum computing moves from research into real world applications, what technical skills and research areas should engineering students focus on today build a successful career?
So as an engineer, it is obviously I did not uh, do an engineering, but as an engineer, you should obviously be focused on the application parts. You should know math as well as what is going to give us the actual products. So what you should focus on is read more about quantum mechanics, but also read up more about how we can make it into reality, because theoretical people, we don't really know about that a lot. So math, a lot of math, stronger math, and then uh, enough quantum mechanics to understand how you can make it a reality. Yeah.
Thank you, ma'am, for that wonderful explanation. And we have a question from our one of our participants. For students who are completely new to quantum technology, how would you explain quantum technology in simple words?
So quantum technology in simple words is we are trying to unlock even more precise, more accurate realms that we have never explored, right? So quantum technology is technology that uses quantum mechanics essentially. But there are obviously, like I explained, there are different principles of quantum mechanics is used for uh, different advantages in each of the fields. So quantum technology is that. Yeah.
Here is another excellent question from our audience, ma'am. What motivated you to choose quantum technology as your research and career field?
Okay, so that's an interesting question. So, like, I started off with quantum information theory, which is a very theoretical field. That was not what my research was. My research was quantum materials. I wanted to know, because if you like, if what I explained from superposition and entanglement, the natural question should be, this person is saying that you cannot observe it, then how does it matter to us? Why should we even be looking into it? We cannot observe superposition states. I made sentences like that, right? That is exactly what interested me. There are we have to very cleverly think of applying quantum mechanics so that it gives us the advantage that we want. So that is why I started off with quantum materials, and now today I'm in quantum communication, which is also like the engineers and the scientists, they sit together and find such like amazing solutions to the problems. Yeah.
And we have another excellent question from our audience. Could you explain the role of photons in quantum communication, ma'am?
Right. So for now, quantum communication is done with photons. So like, how do I say? Uh, like when we talk on call, what takes our sound through the phone and our phone to the other receiver's phone? It's waves, right? It's electromagnetic waves. So light is also like an electromagnetic wave. So light is our medium for transformation of information. So photons are very crucial. And then we manipulate these photons in a way, like I was talking about polarization. That is one uh, property. Yeah, one property of light. So we manipulate that in a way, and then we send it, and then some measurement happens there. So it is the all in all for quantum communication.
With your permission, ma'am, we'll move on to the next question.
Yeah, sure.
What qualities do you think are most important for a student who wants to become a quantum technology researcher?
I think it's curiosity. I mean, it's my opinion, but I think if you have to be curious, and the interesting part of like any research field is that you think you have to. The more you read, the more you think I don't know enough. So how do you deal with that? You just have to stay curious. So I believe that's the only thing that you need, and a little bit of patience. Yeah.
And we also have a wonderful question from one of our participants. Your work also involves quantum materials. What makes a material a quantum material?
That's a very good question. So there, we know about insulators and conductors, right? These are like class 6, class 7, we get introduced to these concepts. So, but uh, these have, there are some materials which have properties which are observed at a very small level. So there are materials which on the big level, they look like insulators. But if we study like each individual, like small sections or small parts, then they start acting like conductors. So these interesting properties show up when we try to, study at the quantum level, which means like at a very small scale. I hope that answers the question.
And ma'am, we are having one more interesting question. How important are Python, MATLAB, programming, and simulation tools for students entering quantum technology?
Mm, Like nowadays, research goes very hand in hand with coding. So we all have to know some language, and for coding, I believe if your foundations are strong, you just have to learn the syntax for every language, right? So what you have to develop is a good understanding of how to solve a problem, and coding is important. Like fairly nowadays, we do use a lot of code. We cannot go anywhere without coding. Python is important. MATLAB, just learn any one very well. I think that is more than enough.
With your permission, we'll move on to the next question, ma'am.
Sure.
How close are we to seeing quantum secured communication being used on a large scale in India?
So, like it was mentioned right in the beginning, we are very close. Like we have already demonstrated um, quantum key distribution, right? So, yeah, at a large scale, we are getting the work started, but we can be optimistic, and I cannot give you a number, but we can be optimistic and say that it's fairly closer than we thought. Yeah.
Thank you, ma'am. And there is one another interesting question. You have specialized in quantum communication. What makes quantum communication different from conventional communication?
So the main appeal of quantum communication is the fact that if there is an third party listener, if there is someone trying to listen to a conversation, then in quantum communication you can guess that you can have an idea if there is someone listening. And for classical communication, it's not possible. I don't think that it's not possible to know if there is someone listening to your conversation. Whereas for quantum communication, if there is someone, they can listen, but it it is very hard for them to listen to the conversation. And the two parties, Alice and Bob, they will know. We make studies of how we think like the eavesdroppers, and then we make the protocols. So scientists who have made these protocols, they think from the eavesdroppers perspective. They give her maximum power, and then the protocols are you know made. So for quantum communication, it's very difficult for another person to hear.
Thank you, ma'am. And one another interesting question from our audience. Looking ahead 10 to 15 years, which quantum technology do you think we have the greatest impact on society? Quantum computing, communication, sensing, or something else?
Impact, if you ask me, the impact on society, then it is going to be quantum computing, because quantum key distribution, again, if I talk about quantum communication, then that's different, quantum communication. But I think it's quantum communication, because computing, because number one is people are looking into it a lot. Quantum communication in India itself, like, there, it's very rare. So people discussing it, people researching it, and companies like ours making it a reality, it's very rare comparatively to quantum computing. So there is a sort of race between the countries in the world to who makes a quantum computer first. So I do not know about impact, but we, like, from the amount of effort being put into the work, I can say quantum computers, like, they might be, it might be the first technology to affect us, like, largely.
Finally, one last question, ma'am.
Sure.
What is one piece of advice you would like to give students who are interested in pursuing a career in quantum technology?
Mm, I think I have, like, in bits and pieces, answered this question. So to reiterate it, like, you should be, you should have a very strong mathematical background, some coding, uh, and have a the, I think the most difficult thing initially is to build the intuition for quantum mechanics. Once you get it done, you, with a little bit of patience and curiosity, I think you can figure out most problems. So I think make your foundation strong, make your foundation strong, stay curious, read up what is happening in the world in the field of quantum technology. That's good enough.
Thank you, ma'am, for patiently answering all the questions and sharing your valuable insights.
No
Now I
problem.
invite our coordinator, Ms. Bhavani, to deliver the vote of thanks. Bhavani, the virtual stage is all yours.
Thank you, Anjali. Good evening, everyone. I'm Bhavani Malge, one of the student coordinator at KIYE Foundation. It's my great honor and privilege to deliver vote of thanks for STOC Lecture 20. On behalf of KIYE Foundation and entire team, I extend our sincere gratitude to our esteemed speaker, Ms. Aditi Das, ma'am. Ma'am, thank you so much for taking out your valuable time today. Your session on quantum communication, quantum information theory, technologies like quantum computing, waves, black body, wave nature, superposition, entanglement was truly inspiring, ma'am. You explained complex topics in such a simple and relatable way. Your journey and the advices you gave to us in Q&A session was like all of us need to think bigger and research with curiosity and dedication. We also learned how important it is to stay updated, keep learning, and contribute to Indians' future in science and technology. That message will carry, ma'am, through our lifetime. I would also like to thank our all respected mentors, dignitaries, and the KIY organizing team, and everyone who worked behind the scene to make this event possible and successful. A big thank you to all the participants as well. Your questions, your energy, and your active participation made this session so interactive and meaningful. As we conclude today's STOC Lecture 20 session, let us take the inspiration forward. Let's keep learning, keep exploring, and keep working towards a strong and self relevant India. Once again, thank you, Ms. Aditi Das, ma'am, for taking out your time with us. You inspired us, ma'am. Thank you so much, everyone, for joining us today. Jai Hind. Thank you.
Thank you. Thank you so
Thank,
much. Thank you for having me. Yeah, sorry. Go ahead, please.
thank you, Bhavani, for the heartfelt vote of thanks. As we conclude today's S Talks Lecture 20, I sincerely thank our esteemed speaker, Miss Aditi Das, for sharing her valuable insights into the fascinating world of quantum technology. Today's session has given us an opportunity to understand how quantum science is moving beyond theory and contributing to the future of secure communication, sensing, defense, and advanced technology. A heartfelt thank you to all our participants for your enthusiastic participation and for making this session a meaningful and engaging one. Stay connected with KIYE Foundation by following and subscribing to our YouTube, Instagram, LinkedIn, WhatsApp, and other social media platforms for updates on upcoming X Talk sessions, internships, workshops, and exciting opportunities. Keep learning, keep innovating, and keep